Oh, welcome to Sunday Science, everybody. I know it's a little weird. It's not on a Monday or a Tuesday, but it is actually Sunday Science, and hopefully we can hold to that a little bit more closely. Anywho, glad to have you all join us again today. We are continuing our climate science series, and we are coming up on Earth Day, so there is, if you're concerned and want more zap, there is an end in sight, and we will get back to lighting stuff on fire and blowing stuff up in our garages.
Yay!
Looking forward to
that. This week we same panel as we've had. I've been incredibly slammed at work lately, so I was not able to put a whole lot of material into this week's episode. But our esteemed panel was gracious enough to go ahead and take care of making sure that the show goes on and that the education is still being shared worldly. So I'm going to hand things over basically right off the bat. I believe Stephen has some pretty awesome stuff about modeling that he would like to share. So I say we jump right on over to you, Stephen.
Yeah, I'll talk about it after the video's over. It's a very dry British video, so I will apologize to our friends across the pond right away. But there are some really important points in it. I'll say until it's over.
Okay, let me just share the video screen so everyone can see it as it's. You guys can see it as it's going. All right, and yeah, you'll just see a black screen till we actually start it. Let me know if any of you fine people on the panel cannot see it. Okay, Steve, here it goes.
I'm Drew Purvis, head of the Computational Ecology and Environmental Science Group at Microsoft Research in Cambridge in the UK. And I spend my days building computer simulation models of plants, animals, and even whole ecosystems. The typical day for us is we would think about something in reality that we care about, whether it's an individual plant or a whole forest or oceans, all kinds of different aspects of the Earth system. And we would be discussing what we think is going on in that system, on the one hand, in reality, and how we can encode that into a computer model on the other hand, so that we can actually simulate that system in a computer. So what is a model and why is it important? What we mean by a model is really a mathematical description of something that occurs in reality. But then nowadays we'll take that mathematical model and we'll put it into a computer program that we simulate in a computer. So a very familiar example might be something like a mechanical model of a bridge, where we have reliable physical models in mathematics and we can simulate the bridge in the computer and see whether it might collapse or not if different things happen to it. But nowadays, because of fast computers and some new statistical methods and so on, we think that it's now possible to do that for much more complex natural systems like plants and animals and even whole ecosystems like forests. In our lab, one of the overarching concerns is the impact of climate change on ecosystems, whether they're approximately natural ecosystems like, let's say, boreal forests, or semi-natural systems like farms and arable fields, pastures, that kind of thing. And so we have a relatively good understanding now of the physical side of climate change. There are still some important uncertainties, but we have a relatively good physical understanding of the impact of carbon dioxide change on the temperature. What we have much less of an understanding of is the knock-on effects of that climate change on natural ecosystems. And so that's something we're looking at many different scales, taking all the data that we can. So nowadays we have amazing data sources available, and then we're coding up models of things like forests and so on, and then we'll change the climate to try to estimate the potential impact of climate change on the forests. One of our biggest projects to date has been a new model of the terrestrial carbon cycle. That model describes all of the flows of carbon between the atmosphere in the form of carbon dioxide through photosynthesis into plants, into the soil and back out into the atmosphere. And that cycle is happening everywhere where there's vegetation. Now, there were previous examples of models of that system, and they had clearly shown that the carbon cycle was potentially very important for the future of climate change. So it could either be a significant brake or a significant turbocharge on future climate change. But the models disagreed. And so what we wanted to begin to do was to take a model, we built a new model, but the main difference was to anchor that model as carefully as we could against as many sources of data as we could get our hands on. And so this model is plausible in the sense that it's consistent with everything that we think we know about the real carbon cycle, but at the same time it's anchored against all the observations and the data. Now at the moment the predictions of that model are still very uncertain, and it's missing some important features like the impact of CO2. So we're only beginning, but we think that we've been able to show that it's at least in principle possible to build a really good, accurate predictive model of something as huge and complex as the terrestrial carbon cycle. There are several reasons for building models of any natural system, whether it's a cell, a plant, or a whole ecosystem. So one of them is that it's a different way to aggregate together what we think we know about that system, what we've learned from the reductionist science, and to aggregate that back together into a model of the whole to see whether we think we approximately understand what's going on, or whether there are some important gaps that we haven't thought about, and so on. So models are important in guiding the science. They can give us new insights into the behavior or perhaps the evolution of that system. We can suddenly realize, oh, this is actually what that system seems to do, especially for something like a whole plant. We might be able to ask, what is it that it's actually evolved to do? And then finally, of course, those models can then make useful predictions. That can be a prediction about perhaps a place we've never visited. So how might wheat yield in a place where it's never been grown? It can be a prediction about the future. So how might wheat production respond to climate change? Or it might be a prediction about an intervention. So how would wheat production change in this place if we were to irrigate, or even if we were to reprogram the behavior of the individual plants? And finally, all of that together gives you, at least we hope, a package for better decision making. Because ultimately, the people that make the important decisions that are going to determine whether or not we all have a sustainable future are not scientists by and large. And so what we hope is that in creating these models and packaging them and communicating them in the right way, we might be able to give the decision makers better information and enable them to make better decisions.
Okay, that's it.
Okay.
All I want to do is talk about, because he did a really good explanation himself, but he went in, the point of this video was to show you the purpose, to explain the purpose of modeling and how to accurately use it to predict things. And as any good model should, it should be able to predict. But he also explained how models can be wrong and how one can take you one direction, one can take you another. And it's very important to remember in modeling, because even a lot of scientists forget this, that if your model doesn't accurately represent reality or has too many open variables, it's a cruddy model. Now, when it comes to climate change, there are so many variables, and there are probably some that we aren't even aware of. But I think it's getting to the point where we have good enough base knowledge and a good number of satellites in orbit that we can actually start watching things and tracking things. And hopefully we can get a good model soon. I think that's all I wanted to say about that.
Well, and with digital models, this is obviously not on the climate change or any sort of GSA work at all, but when it comes to modeling certain things, there's always going to be areas that we don't consider. We're going to have open variables, we're going to have issues, but if we don't model them and then have tested and practical results at the end, there's no way to make modeling better. So I personally don't deal with any finite element analysis when it comes to manufacturing and engineering, but I know that there are more senior engineers above me that do run finite element analysis. And if they're able to, if the software is not capable and it runs a stress testing model, and in a real world situation that just simply is not true, we won't be able to make our software better. We won't be able to improve the accuracy of our modeling, and we won't be able to improve the distance into the future that we're able to predict modeling upon. So a lot of times I think that just because the model's wrong doesn't mean we did anything wrong or that we were wrong entirely. It's that we need to still learn much more information and utilize that information to make our modeling structures and algorithms more complacent with what's actually taking place.
Agreed. But I have seen, the thing is, I have seen scientifically minded people intentionally develop cruddy models. And as someone who deals with people in a certain government agency enough, they recently came up with this, I won't get into too much detail, modeling basically on the movement of benzene in the subsurface. And when I was watching the tutorial, they had so many open variables that we couldn't even consider. And my basic reaction was, why? If you have all these open variables, why are you even attempting to do this? Don't you need more data? Don't you need more, more information? Or is there any way to lower these number of variables? And they're all just like, no, we're just going to use the model. So sometimes there are people do intention, and everything you said is a good point. It's okay to be wrong. It's okay not to know everything, but to sit there and run an intentionally faulty model, it does happen, and people do it, and it's a shame, but whatever, I guess.
Yeah, we are stuck sometimes with that, and it is unfortunate because it's I guess becoming complacent with predicting a failure as opposed to we might be wrong, but we can learn from being wrong much more than we can learn from being right.
That's something that I think we don't have enough of in regard to publishing negative results. And we see that across the board in several different aspects of science, including like pharmaceuticals. So a particular thing didn't do what you wanted it to do, but if it had other negative side effects, that still needs to be published, because if somebody else wants to try to take that particular formulary and utilize it, maybe it's good at something else, but they don't have all of the information associated with the negative side effects. If it's not published and not active knowledge, they don't know that. So there's something that's to be said that's important in regard to publishing stuff that didn't go right. And we don't have enough of that. We need people to be able to publish stuff that doesn't work. So
absolutely,
I agree with that.
Not just because it doesn't work, but because if let's say 10 teams sit down and they run a failed experiment, if they don't publish their findings, there might be another 10 teams that run the same failed experiment. But we already know it's a failure. So if we publish, I was wrong,
and why?
There's nothing wrong with that. There's absolutely nothing wrong with being wrong. But there is something wrong with hiding that information and allowing other people to continue down a path that has already proven to have a null result.
It's pretty interesting. There's a book that I've been reading called Bad Science by Ben Goldacre. And if you're not familiar with the book, check it out. It's really good. He's primarily in medical science, but he talks about a lot of the issues that are associated with this quiet shame that you don't want to publish negative findings because you're not going to get funding. If you have negative findings, you're not going to get grants. You're not going to be able to continue research if you publish stuff that doesn't work. And so even within the scientific community, there's a bit of shaming that goes on if you try to push to publish something that didn't work. And that is a problem. That is a problem within the scientific community that they really need to overcome, because in some cases, somebody else's findings can, even if this is not what we wanted it to do, but these were the results, that can actually save a lot of trouble from focusing, like you said, on research that doesn't work, and is problematic. It's just wasting a lot of time of people that could be focusing on things that work instead of things that don't work, that people didn't have this information because others just sat on it for fear of being shamed,
Indeed, that sounds like a good book. Is there any way we might be able to add that into the description for today's show?
Here, I can get it.
Doc, if you could put it in
the chat. Public chat as well.
So I've been reading it. It's great. And I've been doing my own cognitive bias series. And so it's a lot of parallel that I'm finding that he talks a bit about that too. He has his own website called Bad Science. And so I'll put the website up in the chat as well. So let's see. I know I have to put quotes in there. Hello, everyone. People are saying hi to me. So I put Ben Goldacre's website, badscience.net. He's a pseudoscience buster as well, and he does really good work. He's a really smart guy, and you know, he's actually fine with the pseudoscience market. He's like, if people are going to be stupid and buy stuff like that, that's their money. They're wasting their money. There's a reason why it's $1 billion industry. But do you want to be one of those people? And so he talks a bit about that. So it's kind of cool.
Indeed.
Economic Darwinism?
I don't know how much this affects research science. I've stated 100 times, and I will state 1,000,000 more. I'm an engineer. I don't do research science, but if it wasn't for research science having already existed in certain fields, you know, I don't need to sit down and determine whether I need this part to be made out of aluminum or bronze or phosphor bronze or titanium. Somebody else already did that work. So I don't have to reinvent the wheel every time I design a new piece of equipment. The work's been done.
Right.
If the work didn't, if the research wasn't true, if it didn't hold up to sitting down and actually creating the mechanism, everyone would know a lot more quickly you lied. Some researcher somewhere lied, but that just is with mechanical engineering and how I can relate it. So if in other fields, in cancer research, in climatology, paleoclimatology, there's absolutely nothing wrong with sitting down and going, hey, we really all were hoping this was the case. Maybe it's not. Maybe it's even worse. Findings are findings, and there shouldn't be any shame in what the findings are. I've sat down in front of machine tools with machinists before, and I've said, I swear this is gonna work, and they push that green button, and $100,000 later, we're finally up and running because I screwed up.
Yeah.
And that's fine. There's nothing wrong with that. I thought I was right. I wasn't. We tried it anyways, and there's no shame in being wrong, but there is shame in hiding results. And
yeah,
it's just a bummer to know that there is still so much, shame in a null result, or that feeling of I shouldn't let the world know that this is the case because it makes everything that I've gotten money for pointless.
And it's kind of a scary thing, but it happens a lot in academia because there's just no funding. There's just no funding, especially with the current climate in the U.S. They're gutting science programs like left and right. I left academia. That's one of the reasons why. There's just you can't sustain. You just can't. And so if you're trying to push null results, null findings, you're not going to be as competitive as somebody who's publishing stuff that works. And so it comes down to a bit of business. You have to convince the powers that be that what you're doing is worth it, that you're able to generate results, and you're able to push this research in a forward direction, and and make a difference on some level. And if you're in academia, no results are not effective. They're just not. I don't even know anybody in industry that tries to publish null results, and they have money. So
when it comes to the industry side, I mean, if we do something and it fails, we find a way of fixing the failure. And I'm not, again, like I say, a mechanical engineer. I don't do research science. I take other people's proven science and try and apply it the best I can.
Well, it's applied science.
If something doesn't function, you still have to figure out how to get the product out. You still have to get that end result that is the reason why money comes in. And It's 50-50, you know, it's hit or miss. Sometimes it works, sometimes it doesn't. Sometimes you wind up working 70 hours a week because you have to make it work. You know, so the industry side and the research side are very different, and it's hard to correlate the two. So I'm sure it's very difficult for the monetary sources to recognize the difference between the two.
Yes.
And when you're the wealthy party that's donating your earnings and expecting results out of research, if you pay for something for 5 years and have a null result, you're not going to keep giving money.
Exactly.
It doesn't mean that the research doesn't need to continue. It doesn't mean that we're not on the right path. It doesn't mean that we're not learning and discovering and that it's still viable knowledge that has to get out there. It's just not profitable. So
that's true. And it's frustrating because I think a lot of, and you look at climate science, where you have the people who are in charge of the money are denying that it exists. They're like, climate change isn't real. Why are we spending all this money on it? Why are we spending all this money on climate change? It's not real. It's not important. And we have lawmakers, and I know we don't talk about politics a lot, but if we're going to talk about academia, you know, they're the ones who are in charge of the funding. They're the ones who pick how much money gets to go out to the government-based organizations, and then those government-based organizations have to sit there, and then they're getting heat put on them by other you know, lawmakers, and they're like, well, we need to probably look at this over here and not this over here, and if, you know, they fight back too much, you know, they might get funding cut. So it's a huge societal issue. So it's really hard at times to separate science and politics because of the fact, and also society in general, because we do have a scientific literacy problem, and a lot of society thinks that science is mostly successful, when I would say 90% of it is failure. You don't
I'd say
hear,
we're like 95.
yeah, you don't hear about all the failures. That's what I believe. There's actually a cognitive bias associated with that, where you don't hear about all of the failures, so you think a particular thing is a certain way, or you think,
oh yeah, I mean, even something very basic where you sit down and you have, I don't watch television, so I'm kind of guessing on this one. Maybe you sit down and hop on National Geographic's channel and you hear about how this team has been in the Serengeti for the last 5 years and they got this great imagery finally. Okay, well, that was 30 seconds of film. What about the other 100,000 hours or so that your team put into all of this, that all of this other research was? You don't hear about it. You just don't.
Yeah, you don't hear about all the 90,000 hours of video that they took that was useless.
No, yeah. Sounds like you got a new cognitive bias video to make now.
Well, I mean, there's 20 cognitive biases that I'm working on, and I just finished lesson 15 out of 20, so we got 5 more to go. But yeah, so there's bias associated with that, or outcome bias is one that I haven't done a video yet on, where you essentially, because the outcome was good, the way to get to the outcome, you know, you're like, oh, that wasn't so bad. So for instance, well, I made all this money in Vegas, you know, but that doesn't mean gambling all that money was necessarily a good idea. You know, so it's kind of like, just because you got what you wanted in the end doesn't necessarily mean how you got what you wanted was, you know, not questionable. So science has to avoid outcome bias as well.
Absolutely.
Methods and experiments, all of that. So yeah. But we strayed off topic a little bit.
Just a little bit, but I think it was well worth straying off topic.
Oh yeah, if there was bad information, believe me, I would have chimed in. And so far, you guys have given me no opportunity for that ever.
Okay, let me try again then, Sai. The Earth be flat.
Oh, okay. I'm sorry. That's way off topic and patently silly.
All right.
No,
all right.
no, I'm sorry. The Earth is not flat. It's hollow and expanding.
Oh, that's right. That's right.
Wait,
I
Actually,
forgot it all
get your
changed a couple of weeks ago.
Get your woo-woo straight. Come on.
we better check with Bilu.
Yeah. It's like a freaking balloon, man, and somebody put it into calculations on their computer, which we know you can't have settings wrong for that ever.
Wait, last time I looked at a balloon, it kind of looked like an oblate spheroid.
You know, that particular statement of the oblate spheroid has caused so much contention and given the science deniers so much ammunition. They're expecting to look like an actual pear in space. That's not the
Right.
Oh yeah, and then you tell them it's a geoid, and they look at all the exaggerated topography pictures, and they go, "Oh, whoa! So the Earth really looks like a deformed pear." I mean, yeah, and they use it, and they, yeah, I don't know, but see, that goes back to the importance of modeling. You know, crap in, crap out.
Yes,
you can model anything any
Absolutely.
way you want. If it doesn't match the data and what you have, it's in reality, it's total bunk.
I have a perfect example of that for my own research when I was in graduate school. So the last bit of my master's, I worked in computational chemistry because I was trying to diversify my skill set. And so I was working with the LPA2 receptor, and I had known antagonists that I was working with. I was trying to develop a protocol based on how these particular antagonists interacted with this receptor in what we call MO software. That's molecular orbital environment, I believe is called. So you have your receptor, and I spent an entire weekend running simulations with these antagonists, trying to get it to attach so I could look at the molecular interactions and that sort of thing to kind of see, because the stronger antagonist, I would expect more molecular interaction. I spent the entire weekend and my antagonists were trying to attach to the bottom of my LPA2 receptor and not where it's supposed to go. And so I'm just like, why is this happening? And then there were some that were just completely thrown out altogether that I knew were antagonists. And the software's like, yeah, no, this doesn't work. It's not energetically favorable. I'm like, they have the data. I have the lab data, and I'm trying to replicate it with this software. And the software's like, yeah, no, it doesn't work. And so I'm like, oh my gosh. So garbage in, garbage out. I had a setting off. And so I finally fixed it to where it started attaching in the right place. And the second thing was that there were various, there were isomers of these particular molecules. And since I didn't assign the particular shapes of the molecules, the software was randomly assigning shapes of these isomers, and it was just randomly assigning it to a particular one that was not energetically favorable, and it just was throwing it out. So I had to go in and reassign all of the stereochemistry in order for it to behave properly. So yes, modeling. Oh, goodness.
Yes, modeling. It's important to remember in modeling, it's not like installing a gate or something where if it doesn't fit, force it. If it breaks, it needed fixing anyway.
Yes. And my headphones just died, so I'm sorry if there's an echo. That is my fault. So
It happens. No worries.
See, I took that as an addition to what you were saying, because you had just uttered the word modeling and then took the headphones off and floofed the hair. I assumed it was modeling.
Modeling with the hair.
Indeed. Anyway, okay, you heard it here first. Mel's the next supermodel, up and coming.
Oh man, probably not, but okay.
If anybody wanted to shout off topic, that would have been it. It's a little off topic there.
That's all right.
I'm all for future supermodels being on our show. I have no problem with that. Thank you for joining us, Scientist Mel.
Indeed. Remember us when you're huge. So.
Yeah.
No, you got to say huge.
Huge.
That's what I was thinking. It didn't quite come out that way. Anyway.
So yes, modeling is obviously very important, and outside of scientific models, I know I'm sorry if I'm impeding on all of the work that you guys did on the panel for today's show.
No worries.
Since I was unavailable, but one thing that comes to mind many times is mocking up an assembly. Just because the model isn't perfect and isn't 100%, it doesn't say what the future is. It gives possibilities. It's the same way if you mock up an assembly. So if you're putting together your IKEA table or whatever, you lay the parts out. You look at them. You make sure all the fasteners are there. You take the time to just model it so that then you can actually create it. Or, unfortunately, sometimes when it comes to climatology, destroy it.
Yeah.
So the model doesn't have to be perfect. Chances are not going to be perfect, but it is such a necessary piece of information to take in and to utilize. The thought of going without projection modeling is mind-numbing.
Yeah, I mean, projection modeling is, computer software modeling is very, very useful, especially if you're trying to save money to figure out what parameters and what direction your research needs to go. The reason why we were using computer modeling was to try to be able to find compounds that could initiate an antagonist response for that receptor. So that kind of narrows the field down without trying to stumble over all of the wet lab stuff to figure out which particular compounds are the best ones to explore just blindly. So software modeling does have very, very good uses in regard to trying to figure out where you need to go and which direction is the best way to go, the most feasible from different calculations. So it's a good thing.
Well, and even physical modeling can do just as well with a lot of things. I was recently in a job search and had an opportunity that didn't pan out, but it was actually with the USGS to do physical construction and building of models for dams. Like I say, I was not able to get the job, but sometimes even physical models, it might not replicate exactly what happens in nature, but it gives you an idea of potential points of failure that may exist in an earthen structure. And the same is said for architects that are working with actual scale buildings, aerospace engineers and wind tunnel models. Modeling is a very crucial point of any applied science. And when it comes to research science, I'm sure it's a lot different, but it's still crucial.
Yes, I agree. And when you're dealing with, of course, you have modeling. When you're dealing with engineering, you have to have some kind of even small scale tests and experiments to figure out whether, even if it's in architecture, you have to know what's going to work. And I imagine since you've worked with machinery, you have to have small scale versions of the larger scale versions just to test proof of concept. I mean,
well, yeah, in this day and age, we're dealing with 3D printers, and the 3D printers are actually pretty old when it comes to the work that I do. I've dealt with a lot of SLA work in the past, but that's, that is what it is. There's all sorts of 3D laser sintering of metal components. It's not viable for production work, but there's modeling in that facet. And then there's, like I say, there's sitting down and, very, very basic modeling on architectural scales. How will this building act in the wind?
Yes.
You know, I don't do, like I say, I don't do architecture, but I know that wind tunnel testing is, there's probably more structural engineers that have wind tunnel time than there are aerospace engineers at this point. It wouldn't surprise me. I could be very, very wrong in that, and I'm fine with being wrong, because that just means I can learn something new. But wind tunnel testing is, that's immense, and you have to have scale models, and you have to scale your forces down that you're applying to those models to represent what they would be on the physical scale that they will eventually be. Modeling is very, very important.
Yes, and especially when we have issues now that are coming up with climate change and with the increased amount of heat, flooding. You know, we have storms now that are coming through. There's all these potential issues. That,
how do you even model desalinization of the Atlantic Ocean?
Yeah.
How do we can't sit down and build a scale replica of the Earth.
No,
and then run it through a gambit of experiments within a couple of weeks or so and go, oh, this much fresh water will do this to the North Atlantic current. So we have to model it differently.
Yes, I mean, and you can do living system models and replicate current standards associated with.
I'm just saying, like, I can sit down and I can build a tiny 777 and put it in a wind tunnel, and I can know within a couple of hours of building a miniature Boeing 777 how it's going to react to takeoff speeds. We can't do that on a planetary scale, though.
No, it's
so the modeling is much more complex, and it's a completely different version. It's just sometimes I like thinking about the difference between the application model and the research model, because the research model really isn't that different outside of the fact that we can't build it and test it. We can only model it and take the time to make the measurements.
Right.
And see what the results are that we're capable of measuring throughout time. Whereas with the applicable model, I can build 100 777s at a scale model in a month, and I can test all of them, and it's done.
The problem with climate modeling climate stuff is there are so many additional variables that we're not accounting for, but we don't know exist yet.
Indeed.
That's why the model in people that demand a completely accurate model of what's going to happen in the next 10 years are not going to be happy. They're just not going to be happy.
But those are
what we have is it's got to be a process of continuous improvement. Whenever we have a model that seems to be functioning, what about this? There could be some sort of cascade, some sort of effect based on this unrelated phenomenon that we're noticing somewhere else, and then that's added. And with continuing criticism and continuous improvement, we're going to get closer. But it's such a complex system. I actually shudder to think of exactly what kind of computer you need to effectively run a climate model.
Yeah, and there are even variables that we are aware of, but we don't know when and where they'll occur, such as a massive volcanic eruption, how that could affect it or something like that.
Mm-hmm.
Indeed.
What?
Yeah. Well, and then you can look at the current trends with the variables that you have within the past 50 years and kind of map what the trend is going to be if we have a continued amount of increase in CO2. What's that going to look like? How's that going to affect the ice caps? We have all of the data associated with points in time where there have been measurements of the carbon dioxide in the atmosphere, the behavior of the ice caps, what's gone on with the ocean. So we do have some information, and there may be other factors involved too that haven't presented yet. But so far, the projections that they've had, they seem pretty legit because there is a substantial amount of information. But and you can plug that in to, you can actually generate a computer program to kind of take these trends, and you can kind of compare and see, what does the math show you? Is it exponential? If we have an exponential model where there's an increased amount of carbon dioxide without a foreseeable cap, when are we going to reach that runaway greenhouse effect? You know what I mean?
Oh, absolutely.
I absolutely agree. I think, again, I apologize. I've been very tired this week, overworked, blah, blah, blah. I think possibly what I was trying to get towards was that the acceptance of the, putting the 777 model into a wind tunnel, it's accepted because it's, you watch it take place at the runway, you watched it take place in the wind tunnel, everything was right, everything was dialed in, and then the modeling for what was our climate, the paleoclimatology models, well, no one was there. Well, okay, the future climate models, well, we're not there yet, and you don't know. Well, okay, hold on. Modeling is still modeling. It might have taken 100 renditions of the physical 777 in a wind tunnel to pass testing. That doesn't mean that there aren't 100 models going on when it comes to our climate. There are hundreds upon hundreds, if not tens of thousands of models. So is there a consensus within the modeling? Yes, actually. There is a generalized consensus. And as Stephen mentioned, yeah, we don't know if this volcano is going to erupt. Things of that nature. There are always going to be unhinged variables. But that's just a fact of life. It's
indeed.
Yeah,
well, I'm good with we have enough historical data and present day data and enough satellites floating around that yes, I think the trend information is spot on, definitely. The improvements with being able to account for more interrelationships and more variables that we may not know yet will lend itself. Will enable us to increase specificity. Like at some point in history, I'm hoping we're going to be able to say, "Oh, Farm Belt, if we don't do something right now, you're in trouble." Unfortunately, by the time we get to that level, it's going to be too late.
Yeah.
Well, I had no idea my modeling video would spark such a lengthy conversation.
That's an important conversation.
Oh, it is. I was just saying.
It is, and I might be just saying the same thing over and over. I can't tell anymore. It's modeling is very important, and we should probably move on to something else. And I'm stuck on this, and
okay.
Yeah.
Well, you got a video, right? You got a video we gonna watch.
Well, you know what? To check out the time. I don't know that we could, but first off, it's a little bit. It's about 15 minutes, and I know we're going to have commentary on it. I don't know if we want to push that one off. Well, here's how we can make the decision. Mel, you said you were looking at some stuff. Do you have some stuff? Or
I do have some stuff. I was going to talk about information about what we have with water stress and climate change. So you can go to, and I'll put the link in the side chat. It's NOAA National Centers for Environmental Information.
Oh yeah, I was looking at that earlier when you shared it. That's a great link.
Yeah, so I've got the current information for March with the national overview of what we're looking at for droughts. And the cool thing about this, there's a lot of different projections. Certain areas are going to be flooded more. Other areas are going to be drier. I have a lot of links. So I'm trying to find which ones are the best ones. Where was the one? There was a full report. That's not it. how will climate change affect water? I think this was, here it is. All right, so this particular article, and I'll share screens really quickly so you guys can see.
Okay, can I say something about real quick about where most people get their water from? Because most people think about it. The vast majority of everyone gets their water from groundwater. Yeah, there are surface aquifers, or there are surface reservoirs and stuff like that, but still, the vast majority of us do get it from the ground. All right, I'm done. I just wanted to say that.
Oh, no, it's fine. I do want to mention what we have to think about when we're concerned about water. There's just a few little statistics, and most of you probably already know this. 98% of our water is salty. All right, so we're 98% of the water we have on our planet is salty. That means only 2% is fresh. Of that 2%, almost 70% is snow and ice. All right, and then 30% is groundwater, and less than 0.5% is surface water, like lakes, rivers, watersheds, this sort of thing. And so for certain areas, there is some concern, and I'm going to share screens now so you guys can get an idea. Let's see. All right, so this picture. This was what we were looking at. This is from 1999 to 2007. So we don't have a lot of, as of 2007, we don't have a lot of water stress in these particular areas. And then it started out, you know, we have some, of course, in the more desert type of areas and that sort of thing. But projections for mid-century are getting a little bit scarier. So here is this particular, that's not it. That's not the picture I want. We already looked at that. This is the picture that I want. And it's still not giving it to me. Why is it being a butt? Anyway.
Because you have 9,000 windows open.
That's probably it, you know. I'm going to just zoom in this way and cheat. Okay. So I'm going to zoom in this way. So current projections on modeling show that we're likely to have a water stress index that goes up with percent change compared to 1900 to 1970. And so our western areas, we're looking at a 20% change to where we're going to have considerably less water. Now we look over here on the eastern areas, we're looking at potential flooding issues. So this means we're going to have to address a possible water shortage. Not only that, but we also have to keep in mind this is also going to affect our fisheries. If you're in the South, you know, catfish type of things, they won't be affected so much over here. But if we have fisheries that are out west, we're going to have issues with food. So it's not just a water thing. It's also a food thing.
So you're telling me I'm going to wind up spending an entire week trying to catch a single brown trout that's the size of a fish stick?
Yes.
Because that's basically what I mean. Our trout are tiny. All of our fish in Colorado are tiny.
Here's another article, and I'll put this in the side chat. And this is from Nature, and it's an open article, so anybody can read it. So I'll put this in the side chat really quickly. I like open articles because they allow you the ability to sit there and read through stuff. So this is compounding impacts, excuse me, of human-induced water stress and climate change on water availability. So this particular paper, they're going through and trying to figure out what's going to happen with the terrestrial phase of the water cycle and how it's impacted with water management, human water use, and what kind of impact this is going to have. But we're going to experience water stress similar to the millennium drought that we've had in the past. But if you get a moment, this is not a very hard paper to read. It's terminology that's pretty straightforward. It's not too difficult. But it looks at the Melbourne area in Australia, where most of the water is consumptive or industrial use. And they look at the large reservoirs. So certain areas like Australia, where we don't have, let me see if I can find their map that they put, where they don't have a lot of fresh water outside of, and here's math for you guys that like math, partial derivatives. I don't like those. They terrify me. Partial derivatives, man, that just gives me flashbacks to physical chemistry. Let me see if I can find, I think it was here. Here's their supplemental stuff. And so they kind of show which watersheds that they were focusing on. This is not watersheds, but major reservoirs. And so even though, you know, Australia is surrounded by water, again, it's 98% salt. And so, you know, they're going to encounter lots of different issues, whether it's drought and even flooding. There's some more reports that you can check out. That's not it. That's not it. Here's one. And there's an entire organization called the IPCC. And this is a technical paper for climate change and water that addresses all of the issues that can come up and things that we need to look at. Now, this was June 2008. I couldn't find anything more recent than this, but the trends haven't changed that much. If anything, they're probably getting a little bit worse. Let me put this in the side chat. A little bit of reading if you're worried about water. And this is available for your consumption. But the thing is that Nature paper is pretty cool because it goes through and it kind of picks apart all of the different things that people, primarily in Melbourne, are going to have to do in order to kind of combat potential flooding as well as drought. Because this is going to be an issue now. I'm in an area where we primarily have groundwater, so that's not as big of an issue as other places that don't have groundwater but primarily rely on freshwater sources in lakes, rivers, and that sort of thing.
Just stay away from my Great Lakes up there in Colorado, okay, Andy?
Stay away from the Great Lakes.
I will make sure that I don't take any water from the Great Lakes. We will just keep drying up and not even getting snow.
Okay, good.
But the thing is, I mean, you know, I think I saw a Dirty Jobs episode, and I know that's real science. It's a Dirty Jobs episode where I think it was Lake Erie or one of them, they had managed to clean up all the pollution to the point that the algae grew so much. There was a dude whose whole job was just collecting all the algae because it was mucking up the motors of the boats. So,
yeah, I don't talk about Lake Erie, also known as Erie.
Is that not a thing? Did Discovery Channel lie to me?
No, Lake Erie has a ton of problems, mostly stemming from all the industrialization around it and the fact that the lake on average is only about 50 feet deep. It's not very deep. It's the shallowest of the lakes.
Wow. Yeah.
It seems like a large body of water to be that shallow.
Well, that's what glacial lakes do. They tend to be very shallow. I mean, Lake Superior isn't, but, you know, that's a real lake.
Lake Superior is an inland sea.
Yeah, it basically is. It's probably the only one that was there before the glaciers came, too. Because it's there for other reasons.
Man.
Yeah, I would definitely say Superior has to be on the land, or on the end of being an inland sea. The tidal flows, the whole nine, submarines are in it. That's a different story.
Yeah. I plan on actually observing the tides next time I'm up there, like doing a little measurements for you all and all that stuff. But I got a lot this year on my plate.
Got a lot. Oh goodness. So I mean, but is that not a thing where there's so much algae because it used to be so polluted and they cleaned it up, and because they did such a good job of cleaning it up, all the algae is overgrown?
So we can screw anything up is what you're saying. Anything.
Well, I mean, it's a lesson in that ecosystems there's a delicate balance. I mean, it is a delicate balance, but yeah, I would rather have a too much algae problem than a disgusting lake where nothing grows. So if I have to pick.
Oh, at least algae blooms do help take care of some other unwanted things.
True.
Yeah, but then isn't there also a problem with causing deoxygenation or something of that sort with too much? I know too much algae in a lake kill all the fish. That's that's all I. This is in small local lakes. I've heard. Is this not an issue?
Well,
No,
I mean,
it is an issue.
Huh?
It is an issue.
Mel says no. Shut up, Si.
Oh, I don't know. No. I don't live out there, so maybe not for a giant lake, but it also depends on the size of the lake, I would think.
Indeed.
Yeah, I'm pretty sure when it comes to a lake here, at least on the Front Range of Colorado, the largest naturally occurring lake might be 4 feet deep and 10 feet wide. We don't have lakes. We have reservoirs. They're all man-made.
Yeah.
I have no idea.
It's similar out here at the New Jersey shore. Between every small shore town and the next, there's usually a lake. And it's hard for me to believe that the lakes space themselves out at 1 mile intervals all up and down the coast.
Yeah, the river I grew up playing in, if you did a size by size comparison from Bear Creek to, let's say, the Potomac out east, you wouldn't see Bear Creek. You wouldn't know that it existed.
Huh.
It'd be like setting a proton next to a lump of coal and saying, which one is which? Well, I only see one thing. What are you talking about?
Indeed. All right, so I'm thinking it was a good choice not to pull up and comment on the longer video. It would have gone a tad over.
I didn't think that there would be that much conversation about modeling. I'm sorry if I harped on the same subject over and over.
It's good. Yeah, we can save it till next time and just have a
sure.
Absolutely.
Absolutely.
I can tell you there's about 5 pieces in that video I want to stop at. So.
All right, and let's see.
Indeed, it is a good video, and we should cover it.
Yes, definitely.
Let's see if you guys will, for 1 second, I just have to get a link to Doc Hackensash wants to do a little bit of a plug. Hopefully nobody objects. I don't see anybody objecting, but
no objection here.
No, none here.
I'm not standing up screaming objection. So
alrighty.
Right.
Let me just send him a link here.
Woohoo!
Nope, that's a live chat. The live chat, that's not going to help him much. Hey, he's already in the live chat. I don't think he needs that. Alrighty, here we go.
In case you want to talk to us in the live chat.
Yeah, like you're already doing. Okay. Doc, it's in, check your Discord. I have sent you a link, because you're cool and whatnot. Anyway.
Somebody sent us the link on algae blooms if you're curious. It was via Brian Stevens. While we wait for the Hackensash.
And hopefully he's still around and will be joining us shortly.
Okay. I'll pull up the Science Daily link on algae while we're waiting that Brian sent. An algal bloom or marine bloom or water bloom is a rapid increase in the population of algae in an aquatic system. As more algae and plants grow, others die. Well, they can crowd out other things. I actually planted a lot of creeping phlox in my flower bed out front because I had such a weed problem. They crowded out everything else. But then the weeds, they still are there. And I'm like, you're supposed to crowd out those weeds. I Hackensash has joined us.
Ah, there we go. Okay.
Hello.
Oh,
Doc, let me
hello,
bring up
Hackensash. How's it going?
Let me bring up your graphic here so you can tell people what's what. Let's see. Here it comes. Okay. You're up, Doc. Tell us what this is about.
Fantastic. Thank you very much. I've started an initiative because the world is severely deficient in hugs. We need more hugs. So I've started this initiative called the Quantum Hug Initiative. And the idea is basically that because when you send a virtual hug, all you're doing is moving electrons around, that these hugs can exist in a state of superposition, which means that one hug can be in every place at once, which means that you can send one hug and hug everybody on the planet all at the same time. Even better, if you send one direct to one person, they get hugged by everybody on the planet at the same time. So it's just this silly notion that I have that maybe we could all hug each other a bit more, and this is a way that we can do it virtually without having to have all that sort of contact and all of those things that some people don't particularly like. So on the 1st of June, starting at 8 o'clock in the morning, Universal Time. We just want to get as many quantum hugs out there as we can. That's not to say that we can't send quantum hugs the rest of the time. We just want to get as many in that 24 hours as we possibly can. I've written a blog post about it that should amuse people and has some actual science in it. And no, I'm not doing DPT chakra and going all quantum woo. I really am not. It's mostly a bit of fun, but it's just a way for us all to kind of reach out and be nice to each other for a bit. So I thought it was worth a bit of promotion.
Indeed.
I love that last two sentences there. That's great.
I forget what they were. I'm waffling this. I really should write something for this plug because I'm going on so many channels and so many shows at the moment, just to kind of strong arming my way in and gate crashing into streams just to talk about this. So I should probably write something. What were the last two sentences? I have no idea what.
It says no animals or feelings were harmed during the sending of this hug.
Oh, right.
However, millions of electrons were horribly inconvenienced.
I do like that.
So yes. So there is a blog post. It's not, it's an easy read. It's designed not to be serious at all. It's a bit of fun, but it's a bit of fun that actually might spread a bit of love around the world, and I think we could do with a bit of that. So I'll pop the.
I have to ask real fast. Was that the link that you sent out earlier in the public chat for Hackensash thinking about thinking?
No. The one that I put in the public chat, somebody was asking, one of the members in the Discord was asking about Big Bang cosmology, which is what most of my blog is about. It's about sort of physics, science, logic, counter apologetics, and various sections where I just rant about things that are pissing me off and that sort of thing. But somebody was asking some questions about Big Bang cosmology, and so I was linking into that and saying, go and look at these particular articles because I'll answer your question. So no, this is something else, and I've just popped a link in the live chat there. And I'm sure that Strike, because he's just an amazing guy who kind of, just like looks after everybody. I'm sure he'll pop it in the video description when you're done.
Indeed, I shall. Absolutely.
All right. So thank you very much, and I really must apologise to Mel because I think this must be about the 5th live chat that she's been on in a row where I've come in at the end. I'm sure she must think I'm stalking her by now.
Kool-Aid man. Oh,
conspiracy,
yeah. Quantum hugs.
Does somebody keep saying his name 3 times? What's going on?
Beetlejuice.
Don't.
Oh, well. On that note, what do you think? What do you think, folk? We're at about 6:10. What do you think? Shall we wrap it up? And
that does seem to be about that time somehow.
And for next week, we will save Rapid Arctic Climate Change. What's cloud got to do with it? There's a teaser.
A great title. I love that title.
That actually sounds like a pretty good one to have on Earth Day.
Yes.
Or within a day or so of. Next
Earth.
Sunday is actually Earth Day, isn't it?
Yes, it is Earth-ish Day.
Yes.
Oh, yay! We made it.
Woohoo! Yes.
Yeah.
Okay.
Is there any zap?
Not today. No. I told you I was operating while we only had the maximum 10-inch arcs last time was due to a mismatch in resonance of the two coils. As it turns out, I was actually operating, the primary was resonant on a harmonic of the secondary, so it was still transferring power, just not as much as we'd like. So
it does happen. I'm hoping to have my new MMC built shortly.
Indeed.
We'll see how it goes.
So fear not, Stephen. There will be future injury. Oh wait, no. High voltage. I meant high voltage.
Remember, failures are an important part to experiments. Remember
yes,
that.
and the
Absolutely. I wanted to say actually. In fact, I did say it in the chat, but it never. About null results. I know that there are quite a lot of scientists who really think that we should be publishing null results. If it weren't for the greatest null result in the history of physics, we probably wouldn't have an internet to be talking about this.
Indeed. Alrighty. All right then. Does anyone have anything to add, or shall we call it?
2 plus 2 is 4. That's what I've added today. You're welcome. I will show myself out.
If we hang around too long, someone is going to show up in the chat and deny that, because there's a hell of a lot of other stuff that is so obvious you practically trip over it that's being denied these days. So
well, it depends on which base you're in if we're doing base math.
Oh, that's true. Okay, very good.
Indeed, and Bull Hobo Rasmussen, absolutely correct. Failure is always an option, and yes, Adam Savage, I guess I have to say that.
Indeed.
Well, let's face it, we learn more by failures, because what constitutes knowledge in science, but what isn't true? How is that not failure being success?
Absolutely.
Indeed.
Exactly.
All right. On that note, maybe we should wrap it up. Everyone do have a most entertaining and joyous week.
Yes.
Absolutely. And we look forward to having it all back again next Sunday. Oh, yeah, I really do. Next Sunday, Monday, Tuesday, something to that effect.
That's a day at the end. You're half right.
Indeed. We'll see you all on a day, okay? We'll see you all again on a day. And it will be good. All right. Let us wrap it up. Have a nice evening, all, and hopefully we'll see you all again soon. And thank you very much for joining us, as always.
Yay! Thank you.
And here we go.